Hi, everyone. Thank you for joining. Welcome to our third webinar in our Solar Circuit 2026 series. If you're new here, we're HelioHub. We're a Discord community for undergrads, recent grads, and researchers interested in heliophysics. My name is Claudia, and I'm joined by my colleagues Phoebe and Dan as usual. This summer, we've been hosting a series of professional development workshops and webinars featuring heliophysics researchers and professionals. Today's webinar is the third in our series. If you missed any of the previous workshops, don't worry. You can find the recordings pinned in the programming channel on our Discord server, or you can check out the Coffee's YouTube channel. Also, just if you have any questions during this webinar, please feel free to put it in the chat, and Phoebe and I will get those questions answered for you. And finally, I'm excited to introduce our speaker, Ace Stratton, an aerospace engineer at the UC Berkeley Space Sciences Laboratory. Ace works on the PADRE mission, which stands for the Polarization and Directivity X-ray experiment, an innovative NASA CubeSat mission that aims to transform our understanding of solar flares. I'll let Ace take it away from here.
Okay, great. Um, I will say some of this stuff I definitely geared towards undergrads, so I apologize for any grad students or non-undergrads watching. Let's see. Let me share my screen. Can you see that okay?
Yes, we can see that.
Okay, great. So, yes, PADRE is the solar polarization and directivity X-ray experiment. Today, I mostly want to take you guys into a quick look into the science it produces, but I figured this group usually gets a lot about the science behind space weather, and I thought it might be great to peel back the curtains and give you a peek into the engineering and the years it takes to produce that science. So, that being said, let's get into it. Padre launched on June 23rd, just so you know, if you wanted to see that little edit there on the bottom of this slide. So some background about me. I'm an aerospace engineering and astrophysics graduate from CU Boulder. Go Buffs! While I was at CU Boulder, I got the opportunity to work on two missions. One, I did theoretical Martian science for the MAVEN mission at LASP, which is the Laboratory for Atmospheric and Space Physics. And the second, I was a lead of not the lead, instrumentational lead of the Canvas CubeSat, which recently launched and is working, which is so exciting because I genuinely didn't think it would. Through my career so far, I got to, go travel a lot. I got to give good presentations and meet a lot of cool people in the Martian community, some of whom work at SSL. I got to go to AGU and share those results, which was really exciting. I then took a step away from the Martian limelight, and I chose to focus more on instrumentation and engineering. This came in three forms. One was my senior graduate project, in which we did an Enceladus uh, scanning electron microscope. We did an instrumentation class at Boulder called FEOS, where we built a spectrometer from scratch. And then, of course, I got to work on Canvas. And overall, what I'd like to point out here is a lot of people sometimes ask me, how did you get where you are now? And it's because I had a ton of experience while I was learning in undergrad, which was really useful and helpful. So, who am I today? I'm an aerospace engineer to represented person at the Space Sciences Laboratory at UC Berkeley, California. And if that doesn't mean anything to you, that's okay, because it doesn't mean anything to me. What I actually am, and this is an abridged list, is an integration and testing lead, a ground support equipment lead. I'm also sort of a schedule manager. I'm also sort of the co-systems engineer of Padre, and the lab space manager, and the Enderosat liaison, and the payload operator, and a sounding rocket wrangler, and now sort of a software engineer, and a member of this thing called the Space Committee, which has nothing to do with outer space and everything to do with office space. So as you can see, a person of many roles is what I fill, and you can spot here the small tier of me not having enough time to do anything. So to jump into Padre from there, I want to give you guys some background into and some of the science of Padre. I'll ask for your patience here because I'm not a scientist despite those many roles, so I'll do my best to tell you about the science of Padre. So Padre launched from Vandenberg Space Force Base on July 23rd last year. It is a 12U CubeSat. It's NASA's H4 instrument, and it hosts two science instruments on board, SHARP and Medea, which I'll get into later. And it's a massive collaboration of all of the companies and institutions that you can see here on the right. Currently, both Medea and Sharp are actively taking science data when available, and we're trying to catch those flares, which is great. I think this is the first time I've given this slideshow, and that status means that we're in full science mode, which is great. So PADRE's goal, as we've discussed, is to observe solar flares. Its main goal is to investigate the dominant electron acceleration mechanisms in large solar flares. It's doing that to understand how magnetic energy stored in the solar corona gets converted into kinetic energy of charged particles. Our objective is to determine the degree of beaming of the accelerated electrons in large solar flares. While we're trying to do all of this science, what's important to know is some of the conditions that we need to capture the science. So the first is solar activity. You guys may have heard up until now, if you guys are all heliophysics, that the sun works on 11-year cycles. PADRE is important right now because we were doing our best to launch during solar maximum to increase our chances of catching a solar flare. Additionally, it was a good time to launch because Solar Orbiter is currently orbiting with a duplicate instrument. Well, we're the duplicate of an instrument on Solar Orbiter called STIX, so we can make co-observations with another spacecraft. So two primary reasons for right now. Solar maximum, and there's another spacecraft that we can compare our science to. So the first instrument on board, SHARP, is the Solar Hard X-ray Polarimeter. SHARP consists of a giant solid beryllium cylinder, and those of you who know anything about chemistry knows that's horrifying because it's extremely toxic, and it was very scary installing it. It's surrounded by 8 detector boards. Each detector board consists of 4 cadmium telluride detectors, otherwise known as Timepix 3 detectors. What SHARP does is it takes in X-rays, and as it's spinning, if those X-rays are polarized, they will deflect along the, what's the word I'm looking for? The horizontal plane. So if your light waves come in, let's say vertically because they're polarized or not polarized, if they are polarized, they'll hit the beryllium scatter and they'll scatter along the horizontal plane, and we'll catch them on 2 detectors. If it's not polarized, we'll know because instead of coming in and scattering to just 2 detectors, we'll see it on all of the detectors. So that's the overall goal of SHARP. Medea is the measuring directivity to determine electron anisotropy. It's a straightforward instrument concept. The reason it's straightforward is this is a copy of the STIX instrument. It's quite literally the flight spares, which I'll get into what flight spares are later. So we basically took that, retrofitted it, and put it on PADRE. What's nice is this looks at directivity. So now not only do we have a polarization measurement, but we have energy and direction measurements. So how do we go from this kind of concept? We want to look at solar flares. We want to go look at polarization. And how do we get all the way to the end of science products? Well, this is the beginning timeline. So this is about half the timeline of PADRE. It starts somewhere here in 2022. I can paint you a picture of some scientists going to some engineers and going, I want to do this science project. And then the engineers look at the scientists and they go, you're insane. We can't do that with the engineering things capable. We can do that. And then the scientist looks back at the engineer and goes, no, 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 I think you can do more than you say you can. And thus starts the cycle of eventually getting to a point where you write a proposal. Once you write a proposal, it sits in a proposal cycle for a while. And then we finally get to this 2022 project start. So it's selected and accepted by the NASA H4 program. It then goes through review and design review where you set up the rest of the mission timeline. From there, it takes years to go through prototyping, EM testing, which I'll get into what that is, but engineering model testing, flight model development, and then eventually launch. And after that, science. So I'd briefly like to talk about why PADRE is a bit different. PADRE's whole goal with H4 was twofold. One, can we make a CubeSat a success? Two, how can we make space more accessible with CubeSat? So that means smaller missions, faster development, and more collaboration with commercial vendors. So instead of building everything from the ground up in lab at SSL, we chose a commercial vendor to build a lot of our spacecraft for us. So what does that actually look like? We partnered with Indurosat, who's in Bulgaria, to build this mission. They provide everything other than the instruments. They provided us totally everything. And why would we do that? So it allows us, instead of, spending all of those resources and that time developing the rest of the spacecraft, we got to develop a more complicated instrument. And we allowed the experienced professionals who build that spacecraft over and over and over and over to execute the same thing they've done flawlessly more than once. It's also typically cheaper and it's already space qualified, which is that technology readiness level at the bottom. So PADRE is an example. Everything here on the left is what Indurosat provided. They provided what's called avionics. Avionics here includes solar panels, the structure, the electrical power system. So that includes battery packs and power distribution modules. It includes our communication interface. So how do we actually talk to the ground? It includes our attitude, determination, and control system, which is that ADCS that you see there. And fun fact, for the first ever spinning CubeSat, it has onboard computer, interface, software, ways to look at that software, mission operations, deployers, and launch. So you might be asking, well, that sounds like kind of all of the parts of a spacecraft. So what did you do? So SSL, Goddard, and our partners, we worked on Sharp, Medea, and the power supplies needed to power these very power-hungry instruments. According to our project manager, because of this, we saved about $1 million USD in countless hours. So this is a fraction of the PADRE team, and you might think to yourself, wow, that was a lot of bullet points under the Indurosat side. So this entire image here must be everyone at Indurosat. Would it surprise you to know only this person is from Indurosat? So when I was saying we got to do more complicated instrument development, I meant it. This is the ginormous team and just a fraction of them that it took to develop the complicated instruments we put on board. So this is a blown up view of Sharp, and this just gives you a look into how hard this could be. You're making basically the same thing 8 times over and wrapping it up in a nice package. And you can imagine, one detector and one, let's think any sort of data, like line, right? From, let's say, even a temperature sensor. It's a lot to take in that data at high cadence, deal with it, wrap it up, analyze it, spit it out to the rest of your spacecraft. Now do that 8 times over with 32 individual detectors. So it took a monstrous team to develop this. So we developed the instrument, right? And the rest is history. But yes, but actually no. So I'm now going to give you an abridged view of the steps it actually takes to get to launch, with the notion that it's told from the perspective of someone who is only one of the entire village it takes to get the mission accomplished. So I'm mostly going to talk about these years here and beyond because this is when I joined the team. So the first thing I had to do was I had to learn a completely proprietary system from Indurosat, and I had to make some friends along the way. The reason why is because it's a commercial vendor, but not everything is plug and play. So I had to spend time, requesting the learning materials and documentation, learn that material and documentation does not exist, move on and teach yourself anyways, and then document what you learn and repeat that. And the best part is, in the meantime, you get to build relationships with the people that you're working with so that when you go ask them for help, it's not an email in the void from someone you don't know, it's someone they do know and they're more inclined to help. So part of my job was quite literally becoming friendly and making friends of the people who are our commercial provider. So we had to forge those bonds, and then I had to share knowledge the other way with our new teammates at Indurosat. So bus providers or these commercial providers are pretty new, especially the newer companies are new to science missions, especially ones led by NASA. So we had to review and assist them through their testing campaigns to make sure it was up to NASA standards. So I ended up having to spend maybe 3.5 months in Bulgaria, just sitting by their side, helping them understand like what it looks like when we're here at SSL, what kind of standards we test to. And it's a lot of work. Other than that, if you thought it couldn't get more boring, you also have to manage all the time and resources it takes to accomplish your tasks on time because it turns out rockets don't really wait. They kind of just go when they're ready to go. And so either you're there or you're not, especially when it's a small mission. So this is just a brief glimpse into the hours and hours and hours I had to spend just organizing everything we had to do and making sure it got done. So then you move on to building a test version. This is called the engineering model. You basically build a replica of your flight model and you break it. You try your hardest to break it because if you know how it breaks, you can fix it before it breaks again. So engineering models are used for our most rigorous testing, and used to do the most dangerous testing. So anything where you think, oh, this genuinely might break it, do it to the engineering model first. In best case, you won't destroy it, and at the end, you still have a really useful engineering piece that you can use that I'll show later. So here is a picture of the duplicate of our avionics system because I had to learn how to talk and connect all of those up. And no, it doesn't look pretty because we were in a rush and things were really hard. This is an example of an engineering model of one of our detectors on Sharp. So like I said, it was really complicated. So we had to start with basically one and then slowly work our way up to eight. So all of our testing started with just one. Once you get through building up your engineering model and preparing that, you try, you test, and you fail over and over and over again. You build something like a test setup or an EM detector. You try the setup, you test the setup, you realize it completely failed the test and that you didn't have the correct communication, that something wasn't glued right, that something wasn't assembled right. You learn what went wrong and you repeat that. And here on the right is the morale and happiness of the team trying to adapt some of the Endurosat systems, me, to our instruments. After weeks in a basement where there's chambers and testing chambers, it slowly drives you insane, but it's okay. So we test and then we test, and that's right. We continue testing. It's the reason testing is so, so important is space is as you can imagine, a really complicated and intense environment. So, like I said before, you want to do those tests as much as possible at as early as possible at the limits in space-like conditions. Because the more you learn on the ground, boy, oh boy, is it easier to reach your hands in and fix something than it is to retrieve a spacecraft that's going hundreds of miles an hour around a giant rock in space. So you want to learn everything you can on the ground because what you're doing is unique and you certainly can't brush off anything. And if you do, it's going to have serious consequences. You can ask me how I know later because it had serious consequences. So, what kind of testing? I thought I'd take you guys through a myriad of the tests that we have to do. So, we have control systems on board that make sure we know how to point the spacecraft. How do you test that? You have to get a giant table with air bearing, like a hockey, like the table hockey. You need to get a giant one of those and some giant rings around it that cancel out magnetic fields. And you have to put your whole spacecraft on it. And you check that when you tell wheels to spin to turn your spacecraft, that it actually spins. Then slightly less complicated, we have these fun things called magnetorquers. They affect the magnetic field around the instrument and can slowly turn your spacecraft. The easiest way to test those is to put a compass on it. You can see there's this black bar here in the center, and then you can see that the compass is aligned with it. So we could switch the directions that our magnetorquer was set to, and we could sit there and just watch the compass flip back and forth, which was really fun. Then, of course, we had to deploy systems. So here on the top is a UHF antenna. We had to tie it over and over and over with cute little fishing wire and a resistor, and we had to tell that resistor to get really hot until it melted the fishing wire and the antenna blew out and deployed. Because you really need your communication system to work in space. So we tested that. Then we had to test our detectors and our entire setup in something like this. This is called a thermal vacuum chamber. That's where we get to space-like conditions. So you remove all the air from the system. You set it super cold to the space temperatures you're expecting, and you make sure that everything that was working 5 minutes ago on the bench also works when it's really cold and there's no atmosphere. Spoiler alert, it didn't the first couple times, which is why you do these tests. Some of the most fun testing is what you can see here in this gold box with two pictures. This gold box contains a homemade X-ray beam line because we also needed to make sure that if we had polarization on PADRE, that we would see that it was polarized. So we had to make our own X-ray setup that's in this big scary box with a big scary light because it turns out X-rays aren't particularly healthy for humans. So you have to make sure it doesn't escape anywhere. And then you have to sit there and you have to scan all of your detectors. So that was a lot of fun. Then, once you test all of your instruments, you have to put it all together. And when you put it all together, you can see here is sharp. Can you guys see my mouse? You can just nod. Okay. So you can see sharp here. You can see all of those avionics I was talking about down here. And then we have our big structure. This is where our beam line is. And then we have a little square there in the corner, and that's Medea. So we put everything together, and now we need to test the whole system all at once. We have to make sure that X-rays go in. They go to the instrument. It goes from your instrument board to your instrument interface board. And then once it goes to your instrument interface board, you have to make sure that goes to your onboard computer. Once it goes to the onboard computer, you have to make sure the onboard computer will actually send it to your S-band. Once it gets to the S-band or transmitter to transmit data, you have to make sure it actually transmits that data. So there's two terms for the kind of testing you see here. It's an end-to-end test. You want to make sure all the way from the science event down to the ground station, everything works in order. And then there's another term called a day in the life, where I had to set up a whole bunch of code and I had to tell it, it's nighttime. You're in the sunlight. It's nighttime. You're in the sunlight. And I had to make sure that the spacecraft reacted the way it was supposed to knowing that it was in sunlight and looking at the sun versus being in eclipse where everything needs to shut down so it doesn't draw too much battery power. After that, you do some final testing where you lock some of your engineers. This is Chris Mokel, just so Dan Seven knows. This is Chris Mokel locked in our giant room to access one of the clean TVAC chambers where we had to use walkie-talkies to communicate and make sure that things were set up correctly. Also, fun fact, just moments after this, when I went, are you sure the things are set up correctly? And he went, yes, the things are set up correctly. And I said, are you really sure? Because if the things aren't set up correctly, it'll break. And he went, I promise, it's set up correctly. It was not set up correctly. And we broke things a week before launch. But good news, PADRE's working. So we fixed it, and I can tell you about that later. So after you build it and you test it, you have to load it into this thing, and then you have to drive it all the way down to Southern California. You have to put it on a giant table, and you have to shake it as hard as a launch vehicle will shake. And this is to make sure no bolts come loose, no screws come loose, that your instrument doesn't just break itself, because it turns out launches are really violent, and they really, really, really like to break things. So we tried to break it first. Good news, it didn't break. Then you have to come back and you have to make sure after all of that shaking, are our solar panels still connected in the correct place? So here's where you can see I turned all the lights off in the lab and I shined a really bright light at each solar panel and I made sure that it was reading out like, oh, I see sunlight on the right solar panel, because that would have also really sucked if those weren't connected. Then you have to make sure everything's still communicating okay. This is a thumbs up of relief that after all of the horrible trials we put it through, it worked. And then here was my final step on the project. At approximately 4 a.m., because all of our colleagues are in Bulgaria, I had to march up to the lab. I had to get on a Zoom call, and I had 5 minutes to pull a really important red tag out of the system, change some settings, and then turn it off. The reason being, when you pack up a spacecraft, you need everything to be stowed. But when it comes out, it needs to deploy on its own. It needs to deploy autonomously whenever it turns on. But we didn't want that in the lab, right? So you have a special setting and some special hardware that keeps that from happening. But you have to disable that before launch. So this is me at about 4:30 in the morning, very happy because I just successfully, in 5 minutes, tore out this thing, sent some commands, got some health checks back, and then shut it down as quickly as I could to make sure that it wouldn't do some irreparable deployments right before we sent it off. So, oh, I'm missing a photo. That's in the wrong order. So then a couple hours later, you take it and you pack it up and you fly it, not fly it, you drive it all the way down to Vandenberg. You get to attach it to a rocket. So there's PADRE there in the bottom right corner. And then you get to launch it and it goes into space. And when it's in space, you get a nice little, the same YouTube view you guys get. I hate to tell you, you don't get any special extra privilege. You just have to watch the same YouTube stream that everyone else can look up on YouTube. And you go like this, and you just really, really hope that 20 minutes later you get to see your spacecraft leave the rocket. And it did. And then while you're waiting to hear from it, you do this, which is set up our engineering model because we didn't break it. So now we can test things on the ground still before things go up to space. So it's in space, right? The rest is history, right? It's in space. You've done the thing. Well, yes, but still, actually, no. I am still employed with the PADRE mission a year later, and you might wonder, why is that, Ace? What are you still doing on the PADRE mission? Well, hate to tell you, but the work's not over after launch. So after launch, your spacecraft needs to go through something called commissioning. Commissioning is where you gently wake your spacecraft up and you say, hey, are you okay? Are you all right? Can you deploy this? Can you deploy that? So first, you get your first contact, in which everyone cries almost every single time, who's really invested in the system, where your spacecraft woke up on its own and it beams down to Earth and it says, hello, I'm alive. And you go, oh, thank goodness it's alive. Then we learn about its health. We go, did you survive? Do you have any bumps on your head? And it says, no, I'm okay. And we go, all right, can we deploy your solar panels? And it says, yes. And it deploys the solar panels. And then you can take months just slowly taking it from whatever tumble it's in after it gets out of the spacecraft, because you're in a zero-G environment. There's nothing to naturally really slow it down. And you slowly gain control until you have full control of the spacecraft. You can tell it, point here, and it will point there. And you tell it to spin, and it'll spin. Then after that, your instruments are still off because your instruments are the next most complicated piece on board. So you spend months speaking to your instruments, slowly waking them up, doing the same thing. Hey, are you okay? Can you be powered all the way up? Can you do the science you're supposed to do? And it takes eons to do that. And then finally you get science. So you might wonder why it takes eons to do that. It's because with PADRE, because I'm the payload commander, that's why I'm still here. I get to send these commands. Every hour and a half, you have 10 minutes to talk to it. And you have to do a lot in those 10 minutes. And it doesn't particularly enjoy talking in those 10 minutes either. It has a lot to do and a lot it's trying to do while it's, rocketing over some ground station on Earth. So you send commands, you send them up, and you just wait for a response. And then you have to evaluate that response. In an hour and a half, you have to send a new set of commands. But you can't send too many at a time. So, you're really limited in how much you can work through. Once you're there and you're getting commanding done, the next thing I'm doing all day, every day is making sure it's healthy. So at any hour of the day, it's my job to make sure that every time we get this is like one of 8 screenshots I could have gotten of the report I get given every hour to see, hey, are you fully charged? Are you still charging? Do you have the correct time on board? Is the temperature okay on board? What are my detectors doing? What states are they in? What's going on? And you would think, okay, that's not so bad. Surely things don't happen very often, right? Well, oops, I went a little out of order, but that's fine. You also have to watch the SD card. We only have 8 gigabytes of space, which I'm sure you guys all know is not a lot. So I have to make sure that we're not filling up the SD card so we can still do science. So this is an example of what I'm looking at every day. This is from today. Yes, it's getting close to full. Yes, I'm stressed about it. We're making sure that this number here goes back down to the green. And then I'm sending commands all day. And if you thought commands look super cool, they don't. It just looks like a whole bunch of really disgusting CSVs and a terminal or a command line terminal in Windows where I can talk to our ground stations. So back to the question here, surely it's healthy most of the time, right? I went ahead and I opened my inbox and I just typed in the word anomaly and I hit enter. And I took a small screenshot. This is from the last month of just how many times anomalies happen. So as a payload controller, it's my job, once again, to always be available for this. So I always need to be monitoring this to see if anyone else catches an anomaly before I do. And then we have to diagnose, address, and fix that problem. So If Dan's ever wondering sometimes, why I'm not always up at the lab all the time, every now and then it's because I get an email at 4 o'clock in the morning and I spend the whole day in pajamas with coffee in this chair, going, please don't be broken forever, doing everything I can to make things better and to put it back into science mode. So everything's working, it's healthy. Now what? Now you sit there and you just, like a crazy person, watch the sun. They told you never stare at the sun. I'm convinced I should stare at it every day, except through data. I'm staring at the sun and I'm going, please, 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 big flare. But there's a whole lot of times when, even if there was a flare, we can't capture it, right? Because flares last a matter of minutes, not like hours or days. It's minutes. And there's three places where we can be where we're not going to catch the flare because the background radiation is so high, we won't be able to capture the flare with our own instruments. One of those is the South Atlantic anomaly. I don't know if you guys know what the South Atlantic anomaly is, but it's a place on Earth where our magnetic field is slightly shifted. So there's a lot more radiation at lower altitudes. So PADRE flies through that, and there's a whole bunch of X-rays there. So if there's X-rays there and then there's a big flare on the sun, we can't see it. The SAA is too bright. We could be in one of the radiation belts, so that's at the top and the bottom where we get our aurora. Aurora is so pretty, they're so bad for my science. So you really have to hope you're not there where your auroral regions are. And then you have to hope you're even looking at the sun, because for half of our orbit, we're on the other side of the planet. So Earth's between us and the sun, and we can't see anything, otherwise known as eclipse. So that's what all of these are. You can see all of these times that we're in SAA. Are we in sunlight? Are we in the upper belt? Are we in the lower belt? How much percentage of good observance? You can see about 45% of the time is when we could catch usable science. And then we're just sitting and hoping and hoping and hoping that the sun shows a nice fireworks show for us to capture. And then finally, yay, science. I am not joking. 1 year and 1 month later, on July 4th, the sun had a giant X-class flare event. And for the first time ever, you can see just here, it looks real small. It says good observation, green, true. We got the flare. Both instruments for the first time were on, looking at the sun, and there was a flare. We had a party, let me tell you. The World Cup was already going on. Let me tell you, it got more insane because we caught the flare. But we were still worried maybe the data was wrong somehow. So now, a month later, having gotten that data, gone to take a look at it, I'm happy to give you a preliminary look at some first results of a flare, an X-class flare caught with our SHARP instrument. I do have to add the caveat, because I was requested to add the caveat. Confirmation is still in the works. We're hopeful. This is extremely promising, but we're hopeful that we got it. So here is STIX. That's the Solar Orbiter instrument that we hope to also use Medea to look at it at the same time. So we want STIX to see the flare. You can see STIX sees the flare. And then you want to make sure our detector sees it. And you can see here, as the ghost flare increases, we've got a little bump. That little bump is a flare, and it was 1 year, 1 month, plus the 4 years before that in the making. And everyone can celebrate. Everyone can, throw confetti because we're so happy that we finally got data. So stay tuned. Look to your science publications. Hopefully soon there will be a science publication on huzzah, hooray, PADRE did the thing it was supposed to do that we set out to do. So that's the conclusion of, wow, you guys go, wow, these science instruments are so cool, but it takes so much more behind the curtain to actually deliver you guys that science. But I have some additional conclusions. So first, working on small spacecraft or small missions, I also work on sounding rockets. There's one of my favorite things about it. And because this thing is a sufferfest, it's hard, but I'm not joking, and I know it's corny. If you're a student, you're wondering why you want to stick with this, these are all of my best friends. These are my best friends in the whole wide world. And these are people that I got to go to Alaska, to Colombia, to Bulgaria with, and I got to experience life with them and also suffer. all together because we all care about a common goal. You know, sometimes we get sent to Alaska and we freeze at minus 36 degrees Fahrenheit. Sometimes we go to my least favorite place on Earth, Wallops. I'm slightly joking. Um, you know, sometimes we have to take the night shift because aurora only happened at night. And my other rocket that I worked on studied aurora, so you have to stay up all night. This is when we reported for work at 7:34 p.m. You can tell it was the first night. Uh, and like genuinely, I can't say this enough. These people are my family. I love working on space science just for this fact. Now, the last parting bit I want to give you before we go into Q&A, especially for those of you here who are an undergrad, let's talk quickly about how I got here. I got here because I am crazy. No, not actually, but a little. When I was a freshman, I marched up to Bruce Jakowski, the PI of the Maven mission, and I said, "Give me a job. I love Mars. You're really cool, Bruce. I know you do life on Mars science, and I think Mars is cool. Hire me." And he went, "That's crazy. I've never had a freshman come up with gall, interest, and knowledge. I guess I'll hire her." So I ended up here. And then at some point, I was talking to people at SSL, and I went, "You should hire me because I like this and I like this, and I know that you guys do that. So hire me." And they were like, "Okay, I guess we'll hire you." So, point being, when you send a cold email, this is just a quick rant for students, what not to send. I came across your profile as a research and development engineer at SSL, and I wanted to reach out directly. I would welcome any insight into your current work and whether or not there is a good fit for my background at SSL this summer. I have attached my resume for reference. Let's point out a couple things. I have no idea who this person is because they did not introduce themselves. They are asking me to tell them why they would be a good fit for SSL. I don't know why they'd be a good fit for SSL because I don't know them. They should tell me why they're excited to work at SSL. Also, you know, research and development engineer, that is my first title online, but you can probably come up with more. I saw that you're a research development engineer on PADRE or at SSL, or I really looked and I looked, but I couldn't find a project. Please tell me what projects you work on. I want to know. That would have been great. So, here is what to send in a cold email if you want to send a cold email. Passion and enthusiasm, energy, any amount of care. Word vomit. I don't care. Specifics. What do you want to do? What are your goals? Why and how you found me of all people? And please, literally anything more than what feels like a copy paste from the internet. You know, show some enthusiasm. I did once literally receive 3 paragraphs from an undergrad, and I hired her because it's clear that she was insane and crazy about the job. She wanted it so bad. She was so excited already, not having even been promised anything. And then others I can't remember because it was just a copy paste template from Google. And you know what? Maybe that works in industry, so don't quote me for industry. But if you want to work on things like what I've worked on, this is what I'd recommend. So maybe a little early, but I love questions. Thank you for having me. Thank you, HelioHub, for having me. Thank you for allowing me to go on a brief rant about how undergrads reach out via cold emails. And feel free to contact me. There's my email, but if you contact me, be warned, I will be looking. I will be looking to see if this is a copy paste email. That's all I have. Thank you.
That was fantastic. I thoroughly enjoyed that.
Thanks,
Do
Dan.
you mind if I cut that last part and make a separate little video? Because every day I'm telling students that we have no jobs up here, but there are methods of maybe making a job appear out of nowhere. And you've kind of hit the nail on the head there. It's you
Well,
gotta
like I
know, you gotta like say, I am the person you need, whether you thought about it or not. It's just perfect. So I'd love to post that as its own little separate thing.
Yeah, I agree. I'm always telling students, I'm super busy. You have to convince me that I want to help you because you're so passionate that, like, yes, I want to make sure you get the education. If you don't convince me of that, I don't have time to go make that position or respond to that email.
Right, right, exactly. Well, thanks so much. I really enjoyed that. I do have a few questions, but maybe we should turn it over and see if anyone in our audience has some questions. Um, and usually Claudia and oh, here we have a hand raised. Yes, raise your hand like Alessandra's doing. Alessandra, go ahead.
Hello, I'm Alessandra. I'm actually an incoming freshman at UC Berkeley, and I'm an intended physics major. And I was wondering, like, when thinking about going into research, like my freshman or sophomore year, like, I feel like there are so many different physics concepts that interest me that I don't really know how to pick a specific project because I'm always worried, like, okay, this is interesting, but there's so much more to learn. Like, what if I end up wanting to do something later next year? And so that's so awesome that you had this passion for discovering like this interest in Mars, but how did you decide that that was like exactly what you wanted to do as opposed to other things?
Yeah, I think that's a great question. So I had an interest in Mars, and then I left because I learned through that interest, like through that time, that I didn't enjoy Mars. And I think that's the best part about being an undergrad and in an undergrad position. Now is the time to do that discovery, and there's no better way to discover than, joining interest groups like this. Does it keep piquing your interest? And it's okay if it doesn't. Take an internship and know, usually, especially if people have your best interests in mind, they're going to be okay if you choose to leave. Like Bruce Jakowski respected my decision and was proud of me when I told him, you know what, I enjoyed the science, but I missed the engineering. Like it just wasn't for me. And he's like, I think you made the right decision. So yeah, this is the best part. In undergrad, you get all of this boundless opportunity to work, and it'll be easier than ever to get these positions because, quite frankly, undergrads do not cost that much. So, usually, there's more positions for undergrads. So, go find the one that piques your interest first. Join. If it's not for you, don't be afraid to quit. Quitting doesn't mean that you are a quitter by soul. It means you went, you tried something, you didn't like it, but you learned something. And once you learn something, take that knowledge, go sit down, go, okay, why didn't I like this? What is missing from this? And how can I achieve that? And if I don't know, who can I ask to figure out what I want to look at next? And then go chase the next opportunity. My undergrad took me 5 years. I didn't do it in four because I was taking my time and I would have preferred six. Yeah, I would have preferred six. You've got time. There's no rush. Go enjoy the part where you get to be new to everything because it's the most exciting part. Also the scariest, but the most exciting. So, uh, face the fear, face the uncertain, just pick one that fancies your interest now, and if that changes, that's okay. No one's gonna like write it on your tombstone or anything. It's not a binding contract. You're not forced to keep doing it. You can always switch.
These were you headed on a more of a research path and then became an engineer? Say a little bit more about, your hopes and dreams and then where you ended up and why you made that switch.
It's actually kind of funny. So when I picked a major, I went to a bad high school. Let's put it that way. I went to a very unimpressive high school. So when I picked a major, I went, I want to work in space. What majors have the word space in them? Aerospace has the word space in it, so I'll apply for that. But I was a little too scared to commit to somewhere like Embry-Riddle. That's aerospace, like only. I wanted the option to change, so I picked CU Boulder. And then I was doing aerospace, and they're like, you have to learn about airplane wings, and you have to learn about propulsion. And I was like, whoa, I don't know if that's really what I want to be doing. So I picked up astrophysics on the side, and then I met Bruce Jakowski, and then I went, wow, I actually really like this. And then he was like, you should wait, keep dipping your toes in this before you commit.
Right, right.
And so I went down science and I was ready to abandon engineering altogether. And then my engineering classes finally got better. So he made me wait. He said, once you finish your junior year of engineering, I'll allow you to switch to astrophysics. Well, he couldn't allow me, but
Right, right.
he was like, really don't. I don't recommend it. I finished my interesting classes junior year, and then I had to sit back and I went, Brushkowski, you are right, as you always are. I do really like the engineering. And I learned a lot from the science, but it's not for me. And he went, I know. Go join the
All right.
engineering group. So it was a bit of a ping pong, but I wasn't ready to leave science behind totally. So that's where I ended up actually talking to Rob Lillis a couple times. And I went, hey Rob, how I don't want to leave the science behind, but I want to do the engineering. What do I do? So go back to that part where I was just talking, Alessandra, about I knew what I wanted, but I didn't quite understand the resources to achieve that. So I went and I found someone who might know, and I asked and I said, what do I do? And he said, have you heard of this great thing called instrumentation and small projects where you get to do everything all the time and you get to dip your toes in the science? And I said, wow, that sounds great. So then I went and I found a CubeSat that was doing just that. And I took over the instrumentation on that CubeSat. By just once again having the gall, I just showed up, I was willing to do the work. And then eventually, if you show up and you keep willing to do the work, the person who doesn't really want to do the work will just give you the work. So it's pretty satisfying.
That's yeah. Now you're really living in both worlds, and
Yeah. And
you
then it was,
see that it's interdisciplinary, and you can be just as excited about the science you're doing as the engineering you're doing.
yeah. And it was also crazy because it was my fall semester, 5th year. I took a solar physics class. And I went, this is the coolest thing I have ever learned in my entire life. The sun is so cool. And then that's when I also started targeting like solar missions, like with Juan Carlos.
Wow. There's a
Yeah.
plug for the HelioHub too. Please join our Discord community.
Yes.
We have a lot more people already in their careers in HelioHub lately, which is okay because they serve as good mentors.
All
Uh,
right.
Phoebe, Claudia, any other questions in the chat or any
None in the
questions of the audience?
chat, but does anybody else have a question? Feel free to raise your hand or type it in the chat. Thank you, Ace, for that amazing presentation. That was
Oh,
awesome.
thank you.
Can I ask you, it seems like you're doing mission ops or are you doing um is Sat still doing some of the mission ops for the group?
Yeah, so we've kind of unconventionally split it into two.
Okay.
They do spacecraft ops, so anything that's not the instruments, and I do payload or instrument ops. So we share the same platform and an extreme amount of mutual trust
Okay.
that
Okay.
I will not send commands that affect the spacecraft, and they won't send commands that affect the payloads.
Okay. Is that how you also divide mock and sock?
No, so the SOC tells me what they want done with the payloads.
Okay, okay.
So the SOC, because it turns out being a payload controller is a lot of work and it's very tiring because you're on 24/7. I rely on the SOC to just tell me in plain language what they want done with the
Okay,
payloads.
okay. Was there ever any talk of SSL doing mission ops for Padre, or once you signed up with EnduroSat, you had to go with them?
No, so we actually didn't have to go with them. We were planning on doing mission ops, but a couple things happened. One, SSL mission ops are really expensive. Uh, and EnduroSat mission ops were very not because they had just started doing mission ops,
Okay.
which came with its own host of issues. The fact that we were a guinea pig, that still is coming with its own host of issues.
Interesting.
But additionally, we realized that we had already locked into an S-band transmitter that is favored on a transmission band that is illegal to transmit in the United States. Yes, so it's 43 point something gigahertz, megahertz is a band used for military communications in the United States. So it is illegal for us to transmit to US stations using that, but we can in the rest of the world. So we would have had to go all change our S-band and apply for special US licensing. And both of those also cost a ton of time and money.
Oh, that's crazy.
Yeah,
All
it's
right.
really nuts. That's also what we broke. We broke our S-band.
Oh my goodness. Okay.
And we didn't want to break configuration. So for everyone else, when you break configuration, you have to redo all of your testing to prove it's flight worthy. So we sneakily snuck out one of the counterweights and we put a second S-band transmitter in. And then we just stole the wires from inside and and just bypassed our original. So we're flying with two S-band transmitters.
Oh my
One's dead,
goodness.
and one's the
Okay.
one that we're using.
But I can still post this video, right?
Yeah, totally.
Okay.
I've told this story at AGU. I've told this
Okay.
story in Columbia. It was a great time when Chris Mokel, it was the time of great stress. And Chris Mokel has us all jump on a call at like 7 in the morning. He's like, guys, I have this crazy idea. Lays out the idea, and we go, that's crazy. No way. And then we all sat back for a minute and we went, well, is it that crazy?
It
And
could
then
work.
24 hours later, two people flew from Bulgaria with a new S-band transmitter. We installed it, we retested it, and then we shipped it 2 days after that.
Oh my goodness. Okay. Had EnduroSat worked with a NASA mission previously?
No, we
This was
were
their
there
first.
first.
Wow.
Yeah.
Okay. But NASA didn't put it up a lot of roadblocks.
They did.
Oh, they
We
did.
had to do a lot of convincing, which was part of why I was there for 3 months, so that I could be a
Okay.
first-hand account to NASA in reviews and say, I was there, I saw their test setups, I saw their procedures, I trust what they're doing.
Okay. Maybe they should have done it for free.
Yeah.
That's cool. All right.
Hmm.
Claudia, Phoebe, any questions that you
Yeah.
have?
I was going to ask, you said like how many of the different titles and jobs you juggle at once and that you're pretty busy. What are like your typical working hours in the week, or does it kind of vary just on the season?
Yeah, it varies a lot depending on the season because I am salaried. So something that's really nice is every now and then I really only have to work like half time because I don't have tasks to do. I'm sure there's things I could be doing, but I also need rest. And then there are other weeks like when I'm in Alaska or before launch where I'm working maybe 80 hours a week, including the weekend. So I think up to Padre launch, I worked 4 weeks straight, making sure everything got put together. And then I just didn't work for 2 weeks because I had already worked those additional 2 weeks, like built on top of that time and just kind of went radio silent because it didn't matter because nothing was happening. It was in a car and nothing else could change. So I slept and I got sick and then I was fine.
I was
So,
If it
just
makes
yeah.
sense, splitting up the time.
I was gonna quickly ask, because we have a lot of undergraduate students interested in like NASA missions, which you have worked on. Do you have like any skills that you think are the most valuable to develop for undergrads, and especially like in terms of the coding, is there like a particular like programming language or any skills that you think are valuable to learn?
I think there's no one particular skill in terms of programming language. What is the most important in terms of skill is research ability. So learning how to ask questions. I think that's a lot of things that a lot of undergrads, it takes some time to learn how to actually identify what you don't understand and ask that question. So I think it's always worth asking questions as often as possible because every time you ask a question, you'll learn something about the question you asked and whether it was what you needed. The other one is confidence and the fake it till you make it. Because the other best thing you can do, which is kind of what I've been practicing my entire career, is two-part. Uh, don't necessarily always say yes, but always say you'll try. So when I joined with Bruce, he said, "What's your worst subject?" I said, "Chemistry." He said, "Great, you're doing atmospheric chemistry. Is that okay?" And I said, "Yep, that's fine." Hadn't taken a chemistry class in a long time, but I sat down and I figured it out. And then the other side of that is once you say yes, know when you're in over your head and you actually need to express that to someone and say, okay, wait, pump the brakes. I've gotten in over my head. So I think that skill is like really, really important because I have gained, I don't know how many skills and how many coding languages, and every project I join, they still ask me to do something I've never done before. Doesn't matter. So you can't guarantee skills other than just like the work ethic, the the drive, the know how to ask questions, and the don't be afraid. Just do it anyways. And especially learn how to fail. Learn how to fail. You know, I'm still not the best at failing. I hate failing. I still go cry, like at home, make myself a nice little tea. But the most important part is I get back up the next day and pretend like that never happened. And you keep going because you're gonna have to fail to learn what you need to learn. So learning to accept rejection, failure, all of that. Just keep failing. Don't be afraid to break something. When I joined Padre, Chris Mokel looked at me and he said, if you don't break anything, I don't think you've been trying hard enough. And I said, don't worry. I'll break something. I definitely broke a couple things, but it was okay because that was the point.
Now they're proud trophies. Yeah.
They are proud trophies. I think somewhere I spent 2.5 weeks trying to debug why suddenly PADRE stopped working the flat sat. And so in my office, I have a little uh, framed picture of an SD card that had a hairline fracture through the
And
center because at some point when I popped out the SD card, it snapped and I didn't notice. And I spent weeks tracking down what has happened. I broke a special instrument. No, I touched an SD card a little too hard.
oh my God.
Yeah.
The headache for that, huh?
Oh, the headache.
I can imagine. You had mentioned that Padre is the first spinning CubeSat. Is that true?
At least the first of its kind where we're spinning at a regular rotational rate with good pointing.
Okay, yeah, because then you said you also can point,
Mhm.
but you don't have thrusters on this CubeSat, obviously, right? Yeah.
No, we have 3 reaction wheels and 2 magnetorquers.
So how does something point? Is it constantly spinning and yet
So
you can point at the top or something?
it's looking this way and it's spinning around
Okay.
that. And the answer is our ADCS people called CubeSpace have a mad genius who works for them. And we said we need to rotate at a degree per minute and we need to keep within a degree pointing at the center of the sun. And they
Wow.
said, no, that's not possible. And we said, are you sure? And they went, no. And then I was having drinks with the CubeSpace people at some point, and they were like, yeah, what ended up happening is our boss locked himself in an office with like enough food supply for 2 days, came out. This is what they said. They might be lying, but came out a couple days later and was like, we can do it. We can do it with a special configuration.
Wow.
So some genius in South Africa was really kind, thought that our mission was really interesting and worth the challenge, and figured that out. So I
Wow.
have no idea. All I know is it does it.
That sounds
And
like
it
an
actually does
episode
it
of
really
Star Trek.
well.
That's amazing. Yeah,
Yeah.
you guys should talk to Alan, our Alan Toth is our media PR. Just do a little episode on that. That would make for a great little video or Instagram post or something.
You know what? I should. That's a good
Yeah,
idea.
because it's a great story.
It is. We have so many good stories on Padre. I think I've sat around a couple campfires just telling stories for
Uh,
hours.
Go knock on Alan's door and film one of these stories. That would be great.
Okay.
Well, I think I'm gonna stop the recording now because sometimes that elicits more questions for some reason. But before we end, we again thank you so much. This was quite an honor, and I just found this fascinating. And we'll be posting it on the HelioHub playlist on the Copy's YouTube channel for others to see, where we often get many hundreds of hits. So this will go on and keep living. But thank you
Great.
again, Ace, for taking the time. That was really fantastic of you. Thank you, Claudia and
Thank
Phoebe,
you.
as usual. And with that, we'll say goodbye.